Rational functions. For the rational function of the form y equals a over x minus h, and then plus k, that creates what's called a hyperbola. The parent function of the hyperbola is y equals 1 over x. Notice that x cannot be 0, because if it was 0, I'd be dividing by 0. That's not possible. This creates an asymptote at x equals 0. X equals 0 is the y-axis. So this hyperbola approaches the y-axis on both sides, but theoretically never reaches it. In other words, the y-axis is an asymptote. Also notice that hyperbola has another asymptote, the x-axis. It has two asymptotes. It forever approaches the x-axis but never actually reaches it. Like any other function, we can transform this function. Remember that when you do a horizontal transformation, what happens to the points and what happens in the equation are inverses of each other. If I replace x with x plus 3 you might think would move the graph to the right, but actually it moves the graph 3 to the left. If I replace x with x minus 2, again, you would think it would move it to the left, but because it's horizontal, it actually moves it 2 to the right. With a horizontal transformation, what happens to the graph and what happens to the equation are inverses of each other. That would be right here, plus k. You're either increasing y, this is y, by k, which moves the graph up, it's not the inverse, or minus k would move it down. Remember that only horizontal is the inverse. Plus 1 will move the graph up 1 if k is 1. Minus 1 will move the graph down 1. The most important thing to realize with the parent function is that both the x-axis and the y-axis are asymptotes when you graph a hyperbola. Notice in this example that x got replaced with x plus 2, and it's horizontal because x is being replaced. What happens to the points and what happens in the equation are inverses of each other. So plus 2, rather than moving to the right, moves it to the left. Left 2. And this plus 1 is a vertical transformation. It increases y by 1. That moves everything up 1. See the asymptotes? The asymptotes are x equal negative 2. Notice how if you plug in negative 2 in this equation, it creates division by 0. X can never be negative 2, which is why we have an asymptote at x equal negative 2. And the other asymptote is at y equal 1. Now, you might wonder, why can't we see that in the equation? Well, you actually can if you solve for x. Let's take this equation and solve for x. First, I'm going to move the 1 to the other side. That's y minus 1 equals 3 over x plus 2. I'll put that over 1 and cross multiply. I get 3 equals, cross multiply, y minus 1 times x plus 2. Now I'm trying to solve for x. I'll divide both sides by y minus 1. We'll simplify, and I'm going to turn it around. We have x plus 2 equals 3 over y minus 1. Now subtract 2 from each side, and I get x equals 3 over y minus 1 minus 2. Now you might be thinking at this point, why did you solve for x? Because what I said was you can see y can't be, in this case, 1. Y could never be 1, because if you plug in 1, 1 minus 1 would be 0. Y could never be 1, which is why we have an asymptote at y equals 1. Take a look at that graph again. In the original equation, I can see that x cannot be negative 2 because I'd be dividing by 0. I get an asymptote at x equals negative 2. When I solve for x, I can see that y cannot be 1. I get an asymptote at y equals 1. Now, we don't need to solve for x to see the asymptote. We just need to understand that there's going to be an asymptote in the parent function at both y equals 0 and x equals 0, and then just look at the equation and understand how transformations affect the graph. So here's some properties. Notice that if y equals one function divided by another that's in simplest form, no common factors, you get zeros from the numerator. That's what they're saying the p function is, the numerator. That's because 0 divided by anything equals 0. If I plug in x equal -3, I get 0. And when y equals 0, I get an x-intercept. So there are two x-intercepts, when x equal -3 and when x equal 1. There they are. When the top of the fraction is 0, 0 divided by anything is 0, and you get y equals 0, which is an x-intercept. X-intercepts come from the top of the fraction. Vertical asymptotes come from the bottom of the fraction. That's the q part. I can look at that fraction and see that x can't be 3 because 3 minus 3 is 0. And here I can see that x cannot be -2 because, again, I'd be dividing by 0. It's undefined at that point. That means I'm going to get vertical asymptotes at x equal 3 and at x equal -2. Take a look at this graph. There is the asymptote x equal -2, and there is the asymptote x equal 3. You get some wild looking graphs here. To see what happens, you just need to plug in points and graph those points. We're not going to do a lot of this type of graphing yet, but you need to understand how the numerator and denominator affect the graph. When we graph polynomial functions, we know that vertical asymptotes come from the denominator because you can't divide by 0. That'll create asymptotes, vertical asymptotes, that the graph will forever approach. But what about horizontal? This is what it turns out to be. If your y is two functions that are divided, polynomial functions, notice the top one's the p of x and the bottom one's the q of x, and they have no common factors other than 1. In other words, they're simplified. The graph, at most, has one horizontal asymptote. It turns out if the degree of the top function is greater than the degree of the bottom function, there's no horizontal asymptote. If the degree of the top function is less than the degree of the bottom function, the horizontal asymptote is always the line y equals 0. If the degree of the two functions is 0, then the horizontal asymptote is the line y equals the leading coefficient of the p function divided by the leading coefficient of the q function. Reminder, if I give you a function like 5x cubed plus 2x squared, the degree of this function is 3. It's the degree of the highest term. The leading coefficient would be 5. It's got to be in standard form, that's highest power down. If I had another function like y equal 7x to the 5th plus 2x cubed minus 2x squared plus 1, the degree of this function would be 5, and the leading coefficient would be 7. It needs to be written in standard form, which is highest power down. Take a look at this first equation. Y equals x minus 1 over x squared. Notice that the numerator is 0 when x equals 1, and 0 divided by any number, whatever it might be, is going to be 0. In other words, I know that y will be 0, and that is an x-intercept. A 0 is an x-intercept. Vertical asymptotes come from the denominator, and the denominator is x squared. When I plug in 0, 0 squared is 0. I get a vertical asymptote then at x equals 0. The horizontal asymptote follows this. Since the degree of the top function, which is 1, it has a power of 1, and the degree of the bottom function is 2, the degree of the top function is less than the degree of the bottom function, which is what they're saying right here. That means we're at this one. The horizontal asymptote is the line y equals 0. Second example. The top function factors to x plus 3 times x minus 2. Whenever the numerator is 0, y will be equal to 0, and that will be an x-intercept. When y is 0, those are our zeros. Zeros are x-intercepts. The zeros are at -3 and 2. That's the x-intercepts, -3 and 2. The vertical asymptote comes from the denominator. X cannot be 0 because I'd be dividing by 0, which means my vertical asymptote is at x equals 0. The horizontal asymptote, you look at the degrees. The degree of the top function is 2. The bottom function is 1. The degree of the top one is greater than the degree of the bottom one. That's what they're saying right here. And when that happens, there is no horizontal asymptote. In the last example, y equal 2x squared minus 2 over x squared minus 4. The top has a GCF of 2, and then we're left with the difference of squares, x squared minus 1, which factors to x plus 1 times x minus 1. The denominator is a difference of squares. X squared minus 4 is x plus 2 times x minus 2. Zeros, x-intercepts, come from the numerator. When x equals -1, I get a 0. When x equals 1, I get a 0. Again, that's because 0 divided by any number is always 0, which means y would be 0. Y would equal 0. That's an x-intercept. The vertical asymptotes come from the denominator. I can see that x cannot be -2 and x cannot be 2, because if I plug in -2 and 2 in the denominator, I'm dividing by 0. That's not possible, which means I get vertical asymptotes at x equal -2 and x equals 2. Both of those create division by 0. That's where vertical asymptotes come from. This was a way to write it in one statement. X can't be positive or -2, plus or minus 2. The horizontal asymptote, look at the degree. The degree of the top function is 2. The bottom function is 2. That means that they're equal. And the horizontal asymptote then is the leading coefficient of the top function divided by the leading coefficient of the bottom function, which is 2 over 1, which is y equal 2. Question 1. Graph y equal 1 over x. Graphing these in WAMAP is almost trivial, but you do have to understand a couple of things. First, you need to place your asymptotes. If you forgot what this graph looks like, go watch the first part of the video. It has asymptotes at x equals 0 and y equals 0. That means the y-axis is an asymptote. Trying to dot these things. Asymptote. Take a look at the tables I just put together here. Notice that when I plug in 4, y would be 1 over 4, 1/4. When I plug in 1, y is 1 over 1, that's 1. When I plug in 1/2, 1 over 1/2, you multiply by the reciprocal, it's 1 times 2 over 1, which is 2. And when you plug in 1/4, you end up flipping the 1/4, and it ends up being 4. When you plug in -4, it's -1/4. When you plug in -1, 1 over -1, you get -1. When you plug in -1/2, it's 1 divided by -1/2, and you have to flip that fraction just like we did here. It ends up being -2. When you plug in -1/4, it's 1 divided by -1/4, and you end up flipping the 1/4 and multiplying, and you get -4. This is just a couple of points so you can see what's going on. I plotted those points, and we get those shapes on each side like we expect, and then we try to draw a smooth line through it. When you graph this in WAMAP, as you heard me say, it's almost trivial. But you have to understand the first thing you need to do is place your asymptotes. So click and place the asymptotes, and then you only need to use 2 points in WAMAP. And the very easiest ones to use are these two right here, 1, 1, and -1, -1. When you choose those 2 points, it's going to automatically put it in the graph and you're done. You don't need to graph all these points. You'll need to plot the asymptotes and then graph the 2 points, and it'll automatically place the graph in. It will look very roughly something like this. When you graph the rest of these that are like the parent function y equal 1 over x, always remember the parent function has asymptotes, the x and y axis. That would be y equals 0 and x equals 0. Those are my 2 asymptotes for the parent function. This one's been changed though, but only one asymptote will change. We have a y transformation of down 3. That means the normal asymptote of the x-axis, there's where it would be, is going to get moved down 3. Just imagine that this is the origin and that you're graphing y equal 1 over x. Remember how when you plug in 1, y is 1? And when you plug in -1, y is -1. And when you plug in 2, y is 1/2. And when you plug in 1/2, y is 2. When you plug in -1/2, you get -2. And when you plug in -2, you get -1/2. It's that same exact graph. You only need to plot the 2 points here. So place your asymptotes in WAMAP and then plot the 2 points, and you're done. This one is a horizontal transformation on the parent function, y equal 1 over x. We're replacing x with x plus 2. Remember the horizontal is the inverse. Rather than moving the graph to right, it'll move it to left, meaning that the y-axis is going to shift over, and we'll have an asymptote rather than at x equals 0, that's the y-axis, we'll have one at x equal -2. Everything else is exactly the same, meaning the x-axis is still an asymptote. We've only had a horizontal transformation here. And as I said, just plot those 2 points, 1, 1 and -1, 1, imagining that this is the origin now, right there. And WAMAP will automatically place the rest of the graph. Question 6. Write the equation for the graph below. Y equal 1 over x is our parent function. And we have asymptotes at x equals 0 and at y equals 0 for the parent function. This one still has the same vertical asymptote. X equals 0 is still an asymptote. So we've had no horizontal transformation. We have, however, had a vertical one. We've moved everything up 1. That means our equation is y equal 1 over x, and all we've done is move the asymptote up 1, and there is the answer to question 6. Question 7. Here we've had a horizontal transformation. And we have a horizontal transformation, we're replacing x. We're taking our parent function, y equal 1 over x, which has asymptotes at x equals 0 and y equals 0. And we've replaced x because it's horizontal. We can see that we've had a horizontal transformation. And we know horizontal is the inverse. So rather than being -6, it ends up being x plus 6. There is no vertical transformation because we haven't moved it up or down at all. This is our answer. In question 12, take a look at the equation. We're asked for the horizontal and vertical asymptote. The vertical asymptote comes from the denominator. I can see that x cannot be 1 because I'm dividing by 0, which means I have a vertical asymptote at x equal 1. X equal 1 is the vertical asymptote. There is no horizontal asymptote. Reminder, y equal 1 over x has two asymptotes, at x equals 0 and at y equals 0. We've only had a horizontal transformation, no vertical transformation, which means our horizontal asymptote did not change. It's at y equals 0. Question 14. Vertical asymptotes come from the denominator. I'm going to do that one first. We can look in the denominator and see that x cannot be negative 2, which means we have a vertical asymptote at x equal 2. The horizontal asymptote, this is a different type of function. It's a polynomial function. Notice how the degree of the top one, 1, and the degree of the bottom one, 1, they're equal. That means we're dealing with this one right here. And the horizontal asymptote is the line y equal the leading coefficient of the top function divided by the leading coefficient of the bottom function, which is 3 over 1. That's 1x to the first power, 3 over 1. Y equal 3 over 1, or y equal 3, is a horizontal asymptote. Now, let's check our answer here. The vertical asymptote is x equal 2, which is right there, and that looks good. And the horizontal asymptote is y equal 3, right there, and that one looks good also. Question 16. Vertical asymptotes come from the denominator. This first function is y equal x plus 2 over 3 times x plus 3. It has a GCF. I can see here that x cannot be negative 3, which means I'll have an asymptote at x equal negative 3. For the next one, we're doing the vertical asymptotes only, keep in mind here. It's y equal x plus 1 over 2 times x minus 2. I can see that x cannot be 2, which means I have a vertical asymptote at x equal 2. For the last one, again, we're only doing vertical. It's y equal x cubed plus 1 over 3 times x plus 2. I can see that x cannot be negative 2, which means I'll have a vertical asymptote at x equal negative 2. Question 17. For a polynomial function, horizontal asymptotes follow these rules. We first look to see the degree of the top one. Here it's 3. The degree of the bottom one is 2. The degree of the top function is greater than the degree of the bottom function. That means there's no horizontal asymptote. None. In the second part, the degree of the top one is 2 and the degree of the bottom one is 2. The degree of the two are equal, which means the horizontal asymptote is the leading coefficient of the top one divided by the leading coefficient of the bottom one. 1 over 1. Those are the leading coefficients. The horizontal asymptote is y equal 1 over 1, which is y equal 1. For the last part, the degree of the top function is 2, the degree of the bottom one is 3. The degree of the top function is less than the degree of the bottom function, which means it's this one. The horizontal asymptote is at y equals 0. Question 18. 10x cubed divided by x squared minus 49. We're asked for the horizontal asymptotes first. We know that these are the rules for horizontal asymptotes. The degree of the top one is 3, the degree of the bottom one is 2. The degree of the top is greater than the degree of the bottom, which is this one. There is no horizontal asymptote. It does not exist. Vertical asymptotes, there's going to be more than one because the denominator factors to x plus 7 times x minus 7. It's a difference of squares. So we have two of them. We know that x can't be negative 7. Negative 7 is 1. x equal negative 7, keep in mind, and the other is x equals 7. The two asymptotes are x equal negative 7 and x equals 7. Question 19 asks for the horizontal asymptotes first. Horizontal asymptotes follow these rules. Take a look at the degrees. The degree of the top one is 1, the degree of the bottom one is 2. The degree of the top is less than the degree of the bottom, which is this one. The horizontal asymptote is the line y equals 0. The vertical asymptotes come from the denominator, and the denominator is a difference of squares. It factors to x plus 7 times x minus 7. I can see that x cannot be negative 7. I'd be dividing by 0 if it was. And x cannot be 7. But keep in mind, the vertical asymptotes are lines. They're vertical lines. The lines are x equal negative 7 and x equal 7. In question 22, I've factored the denominators. In the first one, I pulled out a negative 4. You didn't have to pull out the negative. Either way, the asymptote is the same. Negative 4 times 1 minus x is what I made it. The second one, I pulled out a negative 5. Negative 5 times x minus 3. And the third one, you didn't have to, but I pulled out a negative 1. It's negative 1 times x plus 4. It's just a little easier to see what makes 0. These are the vertical asymptotes. I can see in the first one that x can't be 1. So the asymptote is x equal 1. In the second one, I can see that x can't be 3. That means the vertical asymptote is x equal 3. In the third one, I can see that x cannot be negative 4 because negative 4 plus 4 is 0. We have an asymptote then at x equal negative 4. And for the last one, x could not be negative 2. So x equal negative 2 is our asymptote. The horizontal asymptotes follow the rules below. Look at the degrees. For the first one, the degree of the top one is 0. Notice there's no variable. The degree is 0. The degree of the top one is 1. The degree of the top function is less than the degree of the bottom one, which means we're on this one here, and we get y equals 0 is our asymptote. For the second one, the degree of the top and the bottom are equal. Both the numerator and denominator have degree 1. So the horizontal asymptote is the leading coefficient of the top one divided by the leading coefficient of the bottom one, which is negative 10 divided by negative 5, which means we get an asymptote at y equal 2. For the third one, the degree of the top, the numerator, is 2. The degree of the bottom is 1. The degree of the top is greater than the degree of the bottom. There is no horizontal asymptote. It does not exist. And for the last one, the degrees again are equal. So we're to this last one here. The degrees are equal. The leading coefficient of the top, which is 1, divided by the leading coefficient of the bottom is 1. Both numerator and denominator have a coefficient of 1. 1 over 1 then is my horizontal asymptote. That would be y equal 1. Question 23 talks about domain. Domain are the x's. Be aware that how you type this in is very important because WAMAP is not very forgiving. Do not type a period. Type it exactly as it is in the quotes. All real numbers except x is 4, or x is 2, or x is 0. No period, no quotes. Type it exactly what's within the quotes. All real numbers except whatever x cannot be. What you're asking here then is what values can you plug in for x? You can plug in any value for x you want except 0 because you can't divide by 0. So the domain is every number but 0. Type it exactly like that. And the vertical asymptote is from the denominator. We know that x can't be 0 because negative 7 times 0 is 0. It's just x equals 0. The second equation, y equals 4x plus 6, divided by, I'm going to factor it, negative 3 times x minus 2. I can see that x can be any number but 2. So I can plug in any number I want except 2 because I can't divide by 0. So the domain is all numbers but that 2. We know that x can't be 2 because it's an asymptote. That's the line the graph approaches forever. It's at x equal 2. The third graph, y equals 7x minus 5 over 5 times x plus 1, I can see that x can't be negative 1, because if you plug in negative 1, you'd be dividing by 0. X can be any number but negative 1. The domain is all real numbers except negative 1. X can't be negative 1 because it's an asymptote. That's the line the graph forever approaches but never actually reaches. The last one, y equals x over negative x minus 4. You can see here that x cannot be negative 4 because the opposite of negative 4 is 4, and 4 minus 4 is 0. Maybe it would have been better if you factored the denominator and pulled out a negative 1. Negative 1 times x plus 4. Notice that if I distribute the negative 1, I get that. And I can see here easily that x cannot be negative 4. I can plug in any number of this equation I want, except for I can't plug in negative 4 because I'll be dividing by 0. The domain then is all real numbers except negative 4. X cannot be negative 4 because, again, it's the asymptote. It's the line the graph forever approaches but never actually reaches. For question 26, they ask for the y-intercept. You could graph it and figure it out that way, like on Desmos, but it actually turns out not to be that hard. Recall back to when we had a simple linear function like 3x plus 2y equals 12. And when we found intercepts, what we did is we made a table. We knew that if we're looking for the x-intercept, you're on the x-axis and that y is 0. If you're looking for the y-intercept, you're on the y-axis and x is 0. And we made this simple table, and we would plug in 0 for y. 2 times 0 would be 0. 3x is 12. X would have been 4. And then we would have plugged in x is 0. 3 times 0 is 0. 2y would have been 12, and y would have been 6. Keep in mind that if you're looking for the y-intercept, x is 0. If you're looking for the x-intercept, y is 0. If we're looking for the y-intercept in this first example, we know that x is 0. Notice that when you plug in 0, 0 squared is 0, 2 times 0 will be 0, 5 times 0 is 0, and the numerator will become 3. If I plug in x is 0 in the denominator, 0 squared is 0, 0 times 2 is 0, minus 11 times 0, which is 0, and I'm left with 15. Plugging in 0 for x's drops these pieces out, and I get 3 over 15. That's y equals 3 over 15. Notice they're asking for a point. The point would be x is 0, y is 3 over 15. 3 over 15 is 1/5. If we're looking for the x-intercepts, we know that y is 0. This is our y. 0 equals 2x squared plus 5x plus 3 divided by 2x squared minus 11x plus 15. So ask yourself, when would this fraction be 0? And the answer is whenever the top is 0. Then whenever the numerator is 0. The only way to make a fraction 0 is to make the numerator 0. Because 0 divided by anything is 0. When is this numerator, when is it 0? To find that out, we need to factor. This is the harder kind of factoring when there's a number in front. We multiply these two. 2 times 3, we get 6. I need factors of 6. that add to positive 5. That would be 2 and 3. And I'll rewrite the numerator. I'm just factoring the numerator now. It's 2x squared plus 2x plus 3x plus 3, which is 2x times x plus 1 plus 3 times x plus 1. Pull out the x plus 1 out of both terms. It's x plus 1 times 2x plus 3. This is the numerator. Whenever the numerator is 0, the fraction will become 0, and we will get an x-intercept. When x equals -1, that's -1 plus 1 is 0, and 0 times whatever 2x plus 3 is 0, and 0 divided by anything is 0, and y will be 0. We get a point then at -1, 0, that would be an x-intercept. Put a comma between them. And the other x-intercept comes from 2x plus 3. What makes 2x plus 3 0? When is 2x plus 3 0? Move the 3 over. 2x equals -3, divide by 2, divide by 2. Whenever x is -3 halves, we get y equals 0. -3 halves, comma 0 is our other x-intercept. The asymptotes, the vertical asymptotes, come from the denominator. We need to factor the denominator just like we factored the numerator. This is the type with a number in front. We'll take 2 times 15, that's 30. And we need factors of 30 that add to -11. That would be 6 and 5. So -6 times -5 is positive 30, but -6 plus -5 makes -11. Let's rewrite the question then as 2x squared minus 6x minus 5x plus 15, which is 2x times x minus 3 minus 5 times x minus 3. X minus 3, pull that out of both, times 2x minus 5. The vertical asymptotes come from the denominator. We see that x can't be 3. We get a asymptote at x equal 3. X equals 3. Put a comma. There's going to be one more right here. This can't be 0 either. 2x minus 5 can't be 0. Let's find out what value makes that 0. Add 5, 2x equals 5, divide by 2. X cannot be 5 halves. So x equals 5 halves, or 2.5, would be the other asymptote. The horizontal asymptotes follow these rules. The degree of the top, the numerator, is 2. The degree of the denominator is 2. The degree of the two functions is equal. The horizontal asymptote is the leading coefficient of the top polynomial divided by the leading coefficient of the bottom polynomial. That's 2 over 2, or y equals 1. What x-coordinates would there be a hole in the graph of the function? This is question 27. A hole occurs when part of a function cancels out and you can't see it anymore. It's an undefined spot in the function. Notice how in this function the x plus 8's can cancel, but I have to realize that x cannot be -8, because if x was -8, I'd be dividing by 0. The function then is really y equals 4 over x plus 4 plus 5, and I would graph this like normal, but I know that x can't be -8. So somewhere in fact, at x equals 8, you'd have this curve, and there would be an open spot in it, and you get what's called a hole. A hole is an undefined spot in the curve. This would be what you'd graph, but at x equals -8, it's undefined, and you get a hole. X equals -8, then is the answer. Question 32. We're going to graph this. First thing we want to do is factor it. The numerator is -4, times x plus 1, pull out a negative, both signs change. The denominator is negative 2 times x plus 2. We know that we have a 0. A 0 is an x-intercept at x equals negative 1. It's going to hit right here. We know that we have a vertical asymptote at x equals negative 2. Negative 2 is our vertical asymptote. Our horizontal asymptotes, we have to look at the degree. The degree of the top one is 1, and the degree of the bottom one is 1. And the horizontal asymptote, since the degrees are equal, would be the leading coefficient of the top divided by the leading coefficient of the bottom, numerator and denominator. That's negative 4 over negative 2, which is 2. So y equal 2 is a horizontal asymptote. When you graph this, you have to place both asymptotes. The first point you need to put is right here at negative 2, 2 in WAMAP. In WAMAP, you only need 2 points to graph this. If I was graphing this by hand, I'd have to plug in a bunch of values and try different values. But I only need one more point. This graph is a hyperbola. It's very symmetrical. Part of the hyperbola is going to pass through negative 1 and approach these asymptotes. It's going to do the same thing over here. Now, these points will occur here and be mirrored exactly on the other side. If you're not sure what those are, take a look. We can plug in x is negative 3 and x is negative 4 in this function and see what we get. Y equals negative 4 times negative 3 minus 4 over negative 2 times negative 3 minus 4. I'm plugging in x is negative 3. This is 12 minus 4, which is 8, over 6 minus 4, which is 2, and 8 divided by 2 is 4. In other words, we have a point, negative 3, 4, which is right there. And I can tell, and remember you only need 2 points, where my hyperbola is going to be.